In this video for section 4.1, we're going to introduce exponential expressions with this activity about the walkers. In later videos for this section, we will graph exponential functions and use compound interest formulas. So this problem comes from the show The Walking Dead. In The Walking Dead, if a walker bites a human, then the human is turned into a walker. And we can assume that each walker turns one person a week into a walker and none of the walkers are killed. So we're going to use this table to track the human and walker populations over time. So we start with one walker and 139 humans. In week 1, that walker is going to bite a human and turn them into a walker. So now I have 2 walkers and I have 1 fewer human, so 138. In week 2, each of those 2 walkers is going to bite another human. So I'm going to have 4 walkers and 136 humans. In week 3, I'm going to have 8 walkers and 132 humans. Notice that the total number of walkers plus humans is always going to be 140. In week 4, I'll have 16 walkers, and that means that I will have 124 humans. In week 5, I'll have 32 walkers, and then that means I'll have 108 humans. In week 6, I will have 64 walkers, and so my number of humans will be 76. In week 7, I will have 128 walkers, and that means that I will only have 12 humans. And then in week 8, all of these remaining 12 humans will be turned into walkers, and so I will have 140 walkers with no humans left. So how does the walker population change each week? So each week, my walker population is doubled, or it's multiplied by 2. And how long will it take before everyone in town is a walker? Well, that will happen at some point during week 7. Now we're going to do another example where we're starting with 3 walkers. And so in our first week, each of the 3 walkers is going to bite a human. And so we're going to have 6 walkers. And that means that we're going to have 134 humans. After week 2, each of those 6 is going to bite another human and turn them into a walker. So I will have a total of 12. And then my total number of humans is going to be 128. Then I will have 24 walkers in the next week, and that means that I'll have 116 humans. In week 4, I will have 48 walkers, and that means that I'll have 92 humans. In week 5, I will have 96 walkers, and that means that I will have 44 humans. And then in week 6, those 44 will all be turned into walkers, and so I will have 140 walkers with no humans left. So how long will it take for everyone in that town to be a walker? It will happen sometime in week 5. So now we're going to consider what will happen if there were an infinite number of humans in the town. So instead of having a limit of 140 people, what if the number of humans was infinite? So in week 8, what I could do is I could sort of keep multiplying here. So if I go from week 5 to week 8, I would multiply by 2. That means that in week 6, I would have 192. Multiply by 2 again, and multiply by 2 again to get the number in week 8. So I'm going to pull over my Desmos Scientific Calculator here because the numbers are getting a little bit big for me to do on my own. So if week 5 was 96, then week 6 is 96 times 2, which is 192. Week 7 is 192 times 2, 384. And week 8 is 384 times 2, which is 768. Now, to find the number in week 13, I could continue that process, multiplying by 2, or I could start to notice that there's some patterns here. So what I see in the table is that I know that each week I am multiplying the number by 2. So I'm going from week 0 to week 1 is times 2. Going from week 1 to week 2 times 2. Going from week 3 to week 4 times 2. So the number of factors of 2 in my total is the same as the number of weeks. 6 is 2 times 3. 12 is 2 times 2 times 3. 24 is 2 times 2 times 2 times 3, etc. So for week 13, I would have 13 2s and I would have 1 3. So in other words, I can calculate it by doing 2 to the 13th and then multiplying that by 3. That gives me 24,576. Oops. And for week 24, again, I could keep multiplying by 2 on my calculator several times, or I can just change my power here. So in week 24, and I'm going to have 24 factors of 2 multiplied by that initial factor of 3. We have, let's see here, 50,331,648. So for any week, I can figure it out by multiplying 3 times 2 with the power of the week number. And finally, for number 7, we have the equation y equals 6 times 3 to the x. So what do the 6 and the 3 tell us about the walker population in this area? Well, if we go back to what we had up here, the 3 was the initial number of walkers that we had in week 0. So that's why we only had the one factor of 3. The 2 was how much it was increasing by each week. Each week it was multiplied by 2. So for this equation, 6 is going to be the initial number of walkers. And 3 means that my number of walkers is multiplied by 3 or tripled